Oh, wow. Okay, that's pretty interesting. So thanks everyone for coming. So I'll be telling you about watermarking and Trator tracing for pseudorandom functions. And much of this work is joint with Rishabh, Sam, and Brent. And towards the end of this talk, I'll talk more about how we instantiate a lot of the underlying building blocks from lattice-based assumptions. So when we get there, I'll introduce the constructions then. So let's, okay, that didn't work. So let's begin by recalling the notion of software watermarking as has been defined in the literature so far. So in a software watermarking scheme, the goal is as follows. We have a piece of code or a software, and our goal is to embed some mark within this program in such a way that the marked program still behaves essentially the same as the original program. So I can embed a string, let's say a serial number, a username, the owner's name, within a piece of software such that the resulting code still operates exactly as before, but with the guarantee that if somebody comes along with a watermark version of the code and tries and remove that mark from the program, that will destroy the functionality of the program. So somehow the mark is fundamentally tied to the operation of the software itself. So the canonical applications that has been proposed for studying and realizing software watermarking is about things like proving the ownership of the software. If I own the software, I can embed my name or some ID within it so that if somebody steals my software and uses it for unauthorized purposes, there will be some way of identifying that that software indeed belongs to me. Other settings where this has been used is in protecting against unauthorized redistribution of software. This is very conceptually similar to the setting of Trator tracing, which I will also discuss later on in this talk. So just to make sure that we're on the same page regarding what a software watermarking scheme does, it's usually parameterized by two main algorithms. There's a marking algorithm that first takes as description a program. And in this talk, we're going to model programs as Boolean circuits. So it takes as the description a Boolean circuit C, and it takes in some message M. This will be called a mark, and it outputs a marked circuit C prime. And there's also an extraction algorithm that takes as description a marked circuit and either outputs bot, which indicates that the circuit or program is unmarked, or it recovers the corresponding message. So syntactically, basically, there's a mark algorithm that embeds a mark inside a program, and then there's an extraction algorithm that takes the program as input and extracts the actual mark. We can define many different notions. Sometimes you can have the extraction algorithm just have black box access to C prime. In other cases, you can actually have it take in the code of C prime. Here, we'll just look at this very simple schematic for now. So now let me define the prevailing definitions for a watermarking scheme. So the primary notion is this notion of correctness, which basically says that if I embed a mark within the program, the resulting program should behave essentially the same as the original program. So one might ask, why don't we require that the marked version of the program behave identically as the original one? Namely, we don't change the behavior, the input-output behavior of the program. Well, the reason we don't do that is because assuming the existence of indistinguishability obfuscation, perfect functionality preserving watermarking is impossible. And so the resulting works on studying watermarking for software has focused on a relaxed notion of functionality preserving, which just says that the marked version of the program agree with the original one almost everywhere. So for instance, if the domain is super polynomial size, then the points on which the two programs differ should be a negligible fraction of the domain itself. Okay, so the intuitive notion is that I embed a mark in the program, the resulting program still behaves roughly the same as the original one. And the second requirement for a watermarking scheme is basically saying that the mark should somehow be linked to the functionality of the program itself. Namely, an adversary, an efficient adversary that has access to a marked program is not able to produce a new program, let's call it C star here, such that C star and the marked program agree almost everywhere. So namely, it's still functionality preserving on the domain of the program. And yet, the extraction algorithm fails to extract the original watermark. So in particular, if an adversary is able to reproduce the functionality of the program, the reproduced program must also contain the watermark. If the adversary manages to remove the watermark from the program, it must also destroy the functionality. And this seems like a very natural notion of watermarking, namely if I can remove the mark, I must destroy the thing that I was protecting in the first place. And here I want to emphasize that this is actually a fairly flexible adversary. The adversary is allowed to see the code, the description of the marked program itself, and it has complete flexibility in crafting its new program C star, right? So when I talked about it earlier, when I said that the mark extraction algorithm may have either access to the code or an oracle access to the program, when we talk about it from the perspective of the adversary is given a complete description of the code, and even then, it should be hard for the adversary to remove the watermark from the program itself. Okay, so this is a fairly powerful adversary. The only restriction on the adversary is that it has to be efficient, so computationally bounded. So having such a fairly strong adversarial model, it turns out that this notion is only achievable for certain classes of functionalities. And in particular, Cohen et al. In their paper, they showed that this notion is only possible for functionalities that are not learnable. This is not very surprising, simply because if you have an efficient algorithm that can learn the description of a function, just give an oracle access to it, well, then you can take the marked version of the program and learn the original unmarked version, and that immediately gives you an efficient mechanism to remove the watermark from a marked program. So as a result of this impossibility result, much of the work on software watermarking has actually focused on the class of programs that are not efficiently learnable. From a cryptographic perspective, a natural class is the class of cryptographic functions. So as a result of this, much of the work on software watermarking with these strong formal security guarantees has focused on studying watermarking cryptographic functionalities, such as pseudorandom functions or public key encryption, digital signatures, and so on. And that will also be the focus of this work. And in particular, we're going to focus on a symmetric setting, on a secret key setting, where we are watermarking pseudorandom functions. So when I say we watermark a pseudorandom function, what I mean is the program has hardwired inside it a key for a pseudorandom function, and it takes as an input, and it basically computes the output of the PRF evaluated on that point. And the reason that pseudorandom functions are studied is because essentially they are the workhorses of symmetric cryptography. Once we know how to watermark a pseudorandom function, if you now want to say watermark other kinds of symmetric primitives, like the signing algorithm for a message authentication code, the decryption algorithm for a secret key encryption scheme, once you have a PRF, it immediately implies watermarkable notions of these higher level primitives. At least that's what we believe. This is why we focus, or there has been a lot of work on focusing on watermarking these types of functions. Okay, so the first thing I want to do in this talk and is to actually start revisiting this definition of watermarking. So this is we have started out by talking about watermarking general programs. Now we have specialized it to watermarking pseudorandom functions. And the question is, how suitable, or does these kinds of prevailing security notions that we defined, which seem very natural right now, how well do they actually capture the security notion that we might want from a software watermarking scheme? So let's recall this definition of unremovability, which basically, in the setting of watermarking pseudorandom functions, so a special class of functionalities, it says that if nobody is able, so no efficient adversary is able to replicate the behavior of my pseudorandom function, and yet does remove the watermark, right? So if the adversary produces a program that can compute or evaluate the pseudorandom functionality, that program, if it agrees with the original one on most of the points, it has to contain a watermark. But what if we consider an adversary that instead of constructing a program that outputs the entirety of the PRF output, it instead just outputs, let's say, the first quarter of the bits of the PRF, right? So here I've constructed a new program. Let me see if I can get the pointer. Here we have a new program that computes the output of the PRF, but instead of outputting all of the bits of the PRF, we have a program that outputs the first n/4 bits, where n is the output length of the pseudorandom function. So if we consider this new program, well, this new program is not functionality preserving anymore, right? It does not agree with the original function on any point, right? On every single point in the domain of the original function, it disagrees. And yet, at the same time, this new program still captures a lot of important information about the original function. However, the existing definitions for software watermarking says nothing about such an adversary. It can well be the case that on such a program, the watermark is not preserved anymore, and yet, from a conceptual perspective, such a program still carries a lot of information about the original program. Is this ever problematic? No. Right, so basically, we have an adversary circuit that doesn't provide functionality. We have no guarantees under this definition of whether the watermark is preserved in this new program on the right or not. Okay, so does this actually matter, right? Do we actually want a definition to actually capture these kinds of settings? Well, it turns out that in many natural scenarios where we might want to watermark a pseudorandom function or want to watermark such cryptographic functionalities, this could be problematic. So let's consider a standard application that has been proposed for watermarking pseudorandom functions. One thing is we want to protect against the unauthorized redistribution of decryption keys. So this is also a classic traitor tracing scenario. We want to issue many different PRF keys. To each user, we embed their ID within the PRF key. If they now happen to try and leak their PRF key, then we would be able to trace which key was compromised or which key was leaked. So suppose now that we're using a PRF-based encryption scheme. So let's say take your PRF, evaluate encounter mode. This gives you your standard CPA secure encryption scheme. And if we're using it to encrypt, let's say, digital media like images or video content, this is something that what you might see. So now suppose that an adversary comes along, they have a marked version of some decryption device or some decryption key, and they create a new program that essentially outputs the pseudorandom function value, but only preserves the first n/4 bits. It only outputs the first quarter of the bits of the PRF. If I have access to such a program, I can use it to try and partially decrypt this encrypted image. And if you run it, you get what's visualized on the right here. So here, we're not doing any kind of fancy image processing. We're just saying that if we don't know what the output value of the PRF is on a particular bit, we'll just say that it's 0. Otherwise, we will use the decrypted value. You use this key to try and decrypt this encrypted image, and lo and behold, you actually recover a lot of information about the underlying encrypted message. So this should not be very surprising. If we're leaking half, let's say a quarter of the bits of the PRF, we're leaking a quarter of any message that we are encrypting. And this essentially says, or hopefully showcases, that in some sense, a program such as the one that I'm showing here is actually good enough in most settings, right? This doesn't necessarily preserve the exact input-output behavior of the pseudorandom function, but it works well enough to break the security of any application that depends on the pseudorandomness of the PRF, right? And so an adversary that produces such a program that can basically break security of your application, ideally, if we're using watermarking as a way to protect against this kind of behavior, this program should still contain the watermark. So the main takeaway I hope that this example illustrates is that for building blocks like pseudorandom functions for cryptographic functionalities and even for general software, tying the security requirement of a watermarking scheme to requiring that the adversary succeed only by preserving the exact input-output behavior seems like too strong of a restriction on the adversary's ability to try and defeat the scheme. There are many natural scenarios, maybe not just limited to cryptographic ones. Here's an cryptographic example, where the adversary is able to construct a program that still preserves enough information about the original program, and yet may not preserve the exact input-output behavior, and thus would not be captured by existing watermarking security definitions. So in the particular case of PRFs, I argue that exact functionality preserving requirements does not seem like a strong enough security notion. If the adversary is able to break the primitive that relies, let's say, pseudorandomness, then that watermark should, in principle, be preserved. And unfortunately, if we take a look at the existing watermarking constructions that has been proposed in the setting of pseudorandom functions, they actually are not robust against these kinds of adversaries. Namely, an adversary that just outputs the first n/4 bits of the pseudorandom function all of these existing schemes would fail to actually extract the embedded message within the watermarkable PRF. And so if we try and use these watermarkable PRFs as a building block in systems that are relying on watermarking for some kind of protection, those schemes would not be robust against these classes of attacks. Okay, so any questions regarding the definitions or the shortcomings of the existing definitions? Next, I will say how we propose to address these kinds of shortcomings, and in doing so, introduce a new notion that tries to capture and define a much stronger security notion. Okay. All right, so in this work, we propose a notion that tries and addresses many of the limitations and challenges that we perceive in the existing definitions for software watermarking, and in particular for the setting of watermarking pseudorandom functions. Right. So the way that we're going to approach this is we're going to first take a step back, right, and think about what does it mean for what are we trying to protect when we are trying to watermark a pseudorandom function? Well, a pseudorandom function is useful because its input-output behavior is indistinguishable from a random one, right? The security requirement of a pseudorandom function is pseudorandomness, namely that it is indistinguishable from a truly random function. So from a conceptual perspective, it seems like if we want to protect a pseudorandom function or a program that implements a PRF, what we want to protect is the pseudorandomness property itself. Namely, if an adversary is able to produce a program, we don't care what the program does, but if the program allows us or gives us a distinguishing advantage for the PRF against a truly random function, then this program potentially can break the security of any scheme that relies on the PRF, and therefore this program is useful. And if the program is useful, then it should preserve the watermark. So an informal way of viewing our new tracing or new security definition is that if the adversary produces a program that helps it distinguish the outputs of the PRF from a truly random function, then that program must contain the watermark. Right? So of course, this captures the existing watermarking notions, where the watermarking security notion says, if the adversary produces a program that replicates the exact input-output behavior of the PRF almost everywhere, it must contain a watermark. Here we say, well, forget about preserving the input-output behavior everywhere. Just help me distinguish. If you can help me distinguish, we say the program is marked. So let's dive into this definition a little more closely and see how we can actually formalize it. So this is the intuition, at least, in why we take this a perspective in trying to address some of the shortcomings of existing watermarking definitions. This is, of course, very, very similar and exactly the direct analog of Traitor tracing, but specialized to the domain of pseudorandom functions. So I'm not going to go into details here. I think Rishabh gave a talk at the last Lattice workshop on Traitor tracing. So I'll just recall the definition or the notion there. So in a classic setting of Traitor tracing, we're trying to protect decryption keys. And essentially, the security definition there says that if you have a program that is able to distinguish ciphertext encryptions of two different messages, then the tracing algorithm will successfully recover the identity or the mark from that particular program. Here we're doing the same thing, except instead of looking at a decryption algorithm, we're looking at a pseudorandom function. So we're trying to specialize that kind of Traitor tracing definition to the setting of pseudorandom functions. Namely, now if we have a program that can help us distinguish, then that program should contain and preserve the watermark. So let's take a look at trying to formalize this new kind of tracing definition. Again, our initial motivation is that if the adversary who's given a marked version of the circuit produces a new circuit that can distinguish, that should preserve the original mark. So the way that what this will look like is, well, what this distinguisher circuit that the adversary produces is going to play the distinguishing game for the pseudorandom function. What is the distinguishing game? Well, basically there are two different worlds. The distinguisher can make chosen message queries, so it can choose an input X, and in a pseudorandom world, it gets the PRF evaluation at X. In a truly random world, it gets a random function evaluated at X. And the goal of the distinguisher is to figure out which one of these worlds it's living in. So this might seem like a very natural notion. It turns out that this is actually going to be somewhat problematic to achieve. Because if you think about it, the adversary here has a program that can evaluate the PRF almost everywhere, right? So what the adversary can do is just sample a random domain element, X star here, and just hard code C with a single input output of the PRF, right? It just hard codes the input X star and the actual value of the PRF at X star, which the adversary could have computed given its own program. And this is the only thing that C does. C just has one hardwired point in the PRF. And this circuit right here, I claim, has distinguishing advantage that's negligibly close to 1 in the PRF game. Namely, the C just queries on X star, and it checks if the output it gets from the oracle, from either the pseudorandom case or the truly random case, is equal to the actual value of the PRF. Right? So this says that if we have a strong PRF distinguisher, if the PRF distinguisher is allowed to make adaptive queries and compare it against some, let's say, set of values that it knows, it can always break pseudorandomness. But of course, if we only have one single point of the PRF, one single input output of the PRF, C doesn't really have that much information about the structure or the properties of the PRF. It seems very, very difficult, if not impossible, to be able to trace such a circuit C. It seems very difficult to actually be able to extract an identifier. So somehow this definition is too strong. So we have to relax it a little bit. And the way that the relaxation that we consider here is that instead of allowing the circuit C to make adaptive queries of its choosing to either the pseudo-random oracle or the truly random oracle, we instead allow the circuit C only access to the PRF evaluation at random points, right? So instead of allowing C, or the distinguisher that the adversary chooses, to select the points adaptively, those points are sampled uniformly at random, and now it needs to, this distinguisher needs to be able to distinguish the PRF evaluations at random points versus the outputs of a random function. And of course, this is exactly the definition of weak pseudorandomness. So rather than requiring that the distinguisher breaks strong pseudorandomness, it seems very difficult to have a realizable definition here. We instead relax it and say that if the adversary produces a new circuit C that suffices to break weak pseudorandomness of the PRF, namely it has enough information about the global structure of the PRF, basically the evaluations or the input-output behavior of the PRF on a significant fraction of the domain, then that distinguisher can be traced. Namely, we can actually extract the mark from the circuit itself. And here I'll mention that the distinguisher that the adversary produces is allowed to see arbitrarily many input-output pairs. So you can view it as the distinguisher has access to an oracle, and every time it queries the oracle will sample an input and either give the output of the pseudo-random function or the output of a truly random function. So this is the tracing definition that we're going to work with. Basically, if we have a distinguisher that can break weak pseudorandomness of the PRF, then that distinguisher is good. And if it's good, that means the extraction algorithm, the mark extraction or tracing algorithm, will be able to recover the watermark from the program itself. Okay, so let's define everything more precisely so we can reason about the properties and actually construct this primitive. So at a syntactic level, a traceable PRF consists of the following algorithms. There's a setup algorithm that samples the master secret key. This is the secret key for the PRF, as well as a tracing key. And we can consider multiple notions. We can consider the case where the tracing key is a public key, or cases where the tracing key is secret. I'll say a few more words about the constructions in these two different regimes later on. Then there's a marking algorithm that here we'll call key generation that basically takes the PRF key, it takes in an ID, and then outputs a secret key that has the ID embedded inside it. Okay, so this is essentially the ID is the analog of the mark in that watermarking scheme. Then there's an evaluation algorithm, takes in a secret key, takes in a domain element, produces a range element. Here, I'm going to overload this evaluation algorithm for simplicity. The evaluation algorithm can take the actual PRF key or a key for a particular identity. And finally, we have a tracing algorithm that takes in the tracing key, and it only has oracle access to the decoder here, and it produces a subset of identities that could have been compromised or that were used to generate that key. So this is essentially the analog of the extraction algorithm. So let me mention one caveat of the definition that we're proposing here. Here, we're saying that the tracing key is actually sampled in conjunction with the key for the pseudorandom function. And this is kind of implicit or somewhat necessary for this kind of definition, because the tracing algorithm here, in order to use this decoder, right, or sorry, in order to use this distinguisher, it needs to be able to sample input-output pairs of the PRF, right? So essentially, the tracing algorithm has to know some information about the master PRF key. So this is one conceptual distinction with the notion of watermarking, in the sense that the tracing key here has to be completely tied to the PRF key. In watermarking, this is not necessary potentially, but as a result, you end up being able to only achieve a much weaker notion of security, right? If the tracing key doesn't know anything about the PRF key, well, it's not going to be able to use this distinguisher very effectively. In watermarking, we say that, well, because the adversary's program, if it's useful, it has to preserve the input-output behavior. So essentially, a useful adversary program actually gives you that information about the PRF key. Here, we only have a distinguisher. A distinguisher may not give you actual information about the PRF evaluations, right? It may not allow you to actually evaluate the PRF. It can only distinguish evaluations from random or not. So this is actually essential to realizing a much stronger security notion that addresses many of the shortcomings with the existing definitions. Okay, so what are the main properties we care about with a traceable pseudorandom function? Well, all of these are the exact analogs of the definitions we saw for watermarking. So first is correctness, which basically says that the marked key and the unmarked key should agree almost everywhere. So here we have evaluation using the unmarked key, so the master PRF key. Here we have the evaluation using a marked key. And they should agree on all but a negligible fraction of the domain. We can consider stronger notions of correctness, for instance, that these points should be hard to find. For this talk, I'll just focus on this weaker notion where basically on almost all of the points in the domain, the marked key and the unmarked key will agree. Of course, we want pseudorandomness, which says that the evaluation algorithm using the master PRF key should be pseudorandom. Here we can again consider multiple notions. We can say, does it have to be weak pseudorandom or a strong pseudorandom? All of these distinctions are not really essential for this talk. So I'll just work with the simpler definition and just say the evaluation algorithm should implement a pseudorandom function. And finally, we have the analog of unremovability, which we capture by this tracing game. So the tracing game is going to be a game played between an adversary and a challenger. So adversary here, challenger here. For simplicity, once again, I'll just describe the single key setting, where we assume that the adversary only sees a single marked key. So the game then proceeds as follows. The adversary begins by choosing an identity that it wants to get a marked key for. And the challenger will reply by marking the key with the chosen identity. And after this, the adversary's goal is to output a distinguisher. And we basically want to require that if the distinguisher is able to break the weak pseudorandomness of the evaluation algorithm with some noticeable advantage epsilon, then the tracing algorithm will output this identity with probability, again, that's very close to epsilon. So namely, given a marked program for an identity of the adversary's choosing, the adversary cannot produce a distinguisher that is effective and yet does not contain the mark. And once again, we can also consider stronger notions where we give the adversary oracle access to, say, the PRF evaluation and other oracles. But again, I'm just going to focus on a minimal definition that still gives us something very interesting. So for simplicity in this talk, I'll just work with this definition here, where we're not going to worry about additional oracles that the adversary may have access to. In the paper, we provide the definition in its full generality. Okay. So let me just first mention that once we define a traceable pseudorandom function in this way, as a sort of a showcase that this definition is actually useful or gives us meaningful implications, it actually directly implies the Traitor tracing notions for standard symmetric primitives. So for instance, consider our favorite PRF-based encryption scheme, where basically you sample a nonce, you evaluate the PRF on the nonce, and use that to blind the message. Well, if we instantiate this PRF right here with a PRF that satisfies this tracing definition, we see that it immediately implies a secret key Traitor tracing scheme. So namely, we can actually take a traceable PRF and obtain traceable notions of other symmetric cryptographic primitives. If we were to start with a watermarkable PRF, it turns out that this implication is not true, right? Because if we have a watermarkable PRF, the only guarantees it provides is against adversaries that can actually preserve the exact input-output behavior of the pseudorandom function. This does not allow us to construct a watermarkable symmetric decryption devices. And this, I think, is a major limiting factor for studying watermarking for pseudorandom functions under the previous definitions, in the sense that it really just gives us a standalone primitive. We cannot use the PRF as a building block in the context of other primitives and hope that the security properties translate or generalize. With a traceable PRF, it seems much more likely that these kinds of generalizations are possible, because we're saying that any adversary that can produce a circuit that destroys or that distinguishes or breaks security of the PRF, it can be traced. So if we have an application that's relying critically on the security of a PRF, now we have a tracing definition that accommodates and preserves those same kinds of security notions. Okay, so now let me summarize the main results that we show, and then I'll talk about constructions and instantiations. So the first result that we show is that assuming LWE, there exists a single key traceable PRF in the secret key setting. So when I say single key, I just mean the adversary can only see a single identity, so a single marked key. We can consider more general versions where the adversary can actually see multiple marked keys and still is not able to break the tracing security. In this case, we say that the traceable PRF is fully collusion resistant. So assuming LWE, we cannot get a fully collusion resistant traceable PRF. We can only get a single key version, and the scheme supports tracing in a secret key setting. But if we go up and make stronger assumptions, so assuming IO and injective one-way functions, we can get all of the properties we might want. We get full collusion resistance, and we also support public tracing. And the thing that I think is interesting and very notable about these constructions is that the assumptions that we're using, so namely LWE, and in particular, what primitive implied by LWE, this is a notion of a private constrained PRF. This actually is the same assumptions as those needed to realize watermarkable PRFs. So even though we have significantly strengthened the security definition of a watermarkable PRF via this notion of a traceable PRF, we did not need to increase the assumption complexity needed to realize a traceable PRF. So if we want publicly tracing and we want full collusion resistance in the watermarking world, the only constructions are also only known from IO plus injective one-way functions. So in some sense, we're still relying on very similar building blocks, but we're able to use them in a way that gets us much stronger security notions. And in this talk, I'm going to focus, since it's a Lattice seminar, I'm just going to focus on the LWE-based construction and talk about how we build a single key traceable PRF, essentially from private constrained pseudorandom functions. Okay, so the way that we're going to build a traceable pseudorandom function is we're going to go through an intermediate notion. And this intermediate notion is something called a private linear constrained pseudorandom function. And for those of you who are familiar with the Traitor tracing literature and the landscape of Traitor tracing, this is the exact analog of a notion called private linear broadcast encryption introduced by Bonnet, Sahai, and Waters for building Traitor tracing for public key encryption. So here again, we're going to look at this notion, but specialized to the setting of a pseudorandom function. So let me begin by introducing this intermediate notion, and then I will say a few words about how we actually realize this intermediate notion from the LWE assumption. So let's begin with a constrained PRF. So I'm going to parse this one adjective at a time. So let's start with a constrained pseudorandom function. So here we have a PRF. In a constrained PRF, there is a constrained algorithm, and the constrained algorithm takes in the PRF key, and it takes in a circuit C, and it produces a constrained key. Here, I'm just going to worry about circuit constraints. We can talk about smaller or simpler constraint families. Here, it just suffices to think about circuits. So what does this constraint key allow us to do? Well, the constraint key will allow us to evaluate the pseudorandom function on all inputs that satisfy the constraint. So the constraint is a predicate. Basically, it's a function from the domain of the PRF onto 0, 1. And here, we say that the constraint satisfies the predicate if C of x evaluates to 1. So the constraint key can be used to evaluate everywhere where the constraint is satisfied. And if the constraint is not satisfied, then the actual PRF evaluations at those points should still look pseudo-random, even given the constraint key itself. Okay, so I didn't define a security notion here. I just have the correctness requirement. But the security requirement is that we have pseudo-randomness at all points in the domain where the constraint is not satisfied. So we can evaluate where the constraint is satisfied, pseudo-random where the constraint is not satisfied. So in this setting, we are going to be interested in linear constraints. So what is a linear constraint family? So it's going to be defined as follows. First, the inputs in the points in the domain of the PRF, some of them will have a secret index or a secret tag associated with them. And I'll talk a little bit more about this tag later on, but you can just assume that the domain of the PRF can actually be split into two pieces. One is just one may be just like let's say a bit string, but in addition, there is a secret tag, and that secret tag is going to be a number between 0 and 2 to the L. So there's an L bit tag associated with some of the inputs in the PRF. How we use them, I will define a little bit in a little bit later. The second requirement is that the constraint key now is associated with another index, here I'll denote it ID, which is also L bits long, and it can be used to evaluate on all inputs whose index T is less than the ID. So this is why we say it's a linear constraint family, because essentially we have constraint functions that can only be used to evaluate on a subset of the domain. It's a linear subset, right? It's all elements that are smaller than the element in the constraint key. So I think it's a little bit easier. Before I show the visualization of this, let me say one more thing. So the privacy requirement here says that the index that is associated with the domain element is actually hidden. So these details will come together in the subsequent slides. So if it's fuzzy right now, just wait a few minutes and hopefully it will be clarified. Okay, so just to make sure things are clear, let me just reiterate. So input points are associated with some hidden index T. Constraint keys are associated with an identity ID, and it can be used to decrypt all points whose indices are smaller than the identity. Okay, so this is why it's a linear constraint family. If you want to visualize it on a line, we can visualize it like this, right? So here, this line represents the index associated with domain elements of a pseudorandom function. If I have a key for an index ID, I can evaluate on all points in the domain whose indices are smaller than myself. On all points whose indices are bigger than my identity, I will not be able to evaluate. Okay, so this is what I mean when I describe a linear constraint family, constraint PRF family. Finally, we require one more property, which is that there exists a sampling algorithm that allows us to sample PRF inputs with a specific index. Okay, so there are 0 to 2 to the L is the particular index. There exists some sampling algorithm that can allow me to sample a domain element of the PRF with a chosen index. In some cases, this could be a secret key algorithm. In other cases, this could be a public key algorithm. So I think there's a question. So Tamer?
Yes, so I wanted to ask if someone with a constraint key can know whether he was able to evaluate.
Good. Yes, so I haven't defined the security properties on what the constraint key, and what you should be able to learn or not learn given the constraint key. So let me define those 3 security properties first, and then if it's still not clear, please ask a question again. Okay, good. So what should be hidden from the holder of a constraint key? So there are 3 main security properties that we will want. So the first property is that the domain element with index 0. So this index 0 right here. So notice that every key should be able to evaluate a domain element with index 0. All right, because 0 is going to be less than or equal to every index. Elements with a domain 0 are actually indistinguishable from a uniform random element over the entire domain. Okay, so that's the first property. And I should mention that all of these properties should hold even given a constraint key. So I give you a constraint key, you can evaluate, and elements with an index 0 should always be evaluatable. And in fact, not only are they evaluatable, even given a constraint key, you cannot tell that this is an element with index 0. It is indistinguishable from just sampling a random element over the entire domain. The second property is the identity hiding property, which says that if I have a domain element with index I or index j, if you do not have a key that lands in between indices I and j, then you should not be able to distinguish these two domain elements. So if you do have a key that lands between I and j, then this key will allow you to evaluate on one of the points, but not the other point, right? Because remember, the constraint key allows you to evaluate on all points that are smaller than that value. So if you have a key that lands right in between two elements, then that might allow you to distinguish. But if you don't have such a key, you should not be able to distinguish domain elements with those two indices. And finally, the last requirement is that if I have a domain element sampled from the largest index, so this 2 to the L, this the PRF evaluations at this point should be pseudo-random, even given any constraint key, because all of the constraint keys will not be able to evaluate at this particular point. Okay, so the hiding properties that we require are hiding properties on the indices, on the domain indices for the inputs to the PRF. Notice that we do not require hiding properties on the constraint key itself. So if you have a constraint key for, let's say, identity ID, you can read off ID from the constraint key. We do not require hiding for that. So does that answer the question from earlier?
Yes.
Okay, great, excellent. So the constraint key does not hide the identity, but the indices should be hidden in this precise manner. So elements with index 0 are indistinguishable from uniform random elements. So is 2 to the L exponential in a security parameter or polynomial? Good, so that's a great question. So it can be exponential. That means that we can support an exponentially large identity space. It can also be polynomial. So everything I say also works, is actually agnostic to the size of the domain. For simplicity, for the tracing algorithm I will describe, it will be easier to think about it if the identity space is polynomial, but everything also extends naturally to the exponential setting. I'll say a few more words about that when I define the tracing step. Okay. All right, so if we have a private linear constraint PRF with these properties, how can we trace? Okay, so let's take a look at the picture. So the assumption that we're given is that the adversary is going to give us a useful distinguisher, right? So I actually meant to write distinguisher here, not decoder. Decoder, I guess, is from the Traitor tracing language. But here we're talking about PRF distinguishers. So we have a distinguisher D, and it is able to break weak pseudo-randomness with some noticeable advantage epsilon. How can we use this to trace? Well, let's take a look. Suppose first that we sample a domain element with index 0 here. The normal hiding requirement of our private linear constraint PRF says the following. An input with index 0 is indistinguishable from a uniform random element in the domain of the PRF. But now we have a distinguisher that can break weak pseudo-randomness with advantage epsilon. So weak pseudo-randomness says that if I sample a random element in the domain, I can distinguish that, or if I have enough of these elements, I can distinguish them with advantage epsilon. So if the elements with index 0 are indistinguishable from uniform random elements over the full domain, then the advantage of the decoder when I give it inputs with index 0 should be negligibly close to epsilon, right? Because if the decoder works on uniform over the full domain and uniform over the elements with index 0 are indistinguishable from those elements, then a decoder that works here must also work here. Okay, so that's the first property. Second property, let's go to the other end of the extreme. So the pseudo-randomness requirement on a private linear constraint PRF family says that if I sample an element whose index is 2 to the L, so the maximum element in the range or in the identity space, these are pseudo-random. So the decoder should have advantage that is negligible, so negligibly close to 0. Right? So pseudo-randomness should hold regardless of how many constraint keys you have. You can have as many in the collusion resistant setting. So in that setting, you can have arbitrarily many constraint keys. None of them will be able to evaluate the PRF on this 2 to the L index, and therefore those evaluations still look pseudo-random. And so the decoder will not be able to break weak pseudo-randomness with elements whose index is sampled to be 2 to the L. So what do we have now? We have that in this space between 0 and 2 to the L. On the one hand, the decoder has advantage epsilon, has a noticeable advantage. On the very other end of the extreme, the decoder has negligible advantage. So now suppose we do the following. We compare the distinguishing advantage of the decoder at every point along the way. Well, then we know that there must be a jump somewhere, because we went from something noticeable to something negligible. So there must be a jump in the distinguishing advantage between some pair of elements in that interval. But otherwise, so here it's actually conducive to think about L, 2 to the L to be polynomial. So for the exponential case, there's a more sophisticated tracing algorithm that will work. But let's, for a moment, assume that 2 to the L is polynomial in a security parameter. So L is logarithmic in a security parameter. Then, if we just consider every consecutive index along this interval, and one of those intervals, there must be a large jump, right? There must be a noticeable jump. Because otherwise, if this interval has size polynomial and every jump is negligible, we're not going to have a noticeable drop from 0 to the end of the interval. So where can those jumps appear? Well, the final property, which is the third property, is identity hiding. The identity hiding property says the following. If I have an interval I and j that does not contain the index, that does not contain a key that the adversary queried for, the distinguishing advantage can only differ by a negligible amount. The elements, the inputs to those elements are indistinguishable from each other, right? An input with index I is computationally indistinguishable from an element with index j. So therefore, the distinguishing advantage cannot change appreciably noticeably inside this interval. And so with these three properties, we can see that if there is a jump, which there must exist one because of the bookends have a noticeable gap, that jump must appear at an interval that contains the identity element, right? And if that interval contains it, then the tracing algorithm will succeed. So in the case where the identity space, so where L is logarithmic and 2 to the L is polynomial in the security parameter, we can just do a linear scan along this entire interval. We sample indices with index 0, sample indices with index 1, compare the distinguishing advantage, and proceed. The first place where we find a sharp drop or a sharp change in the distinguishing advantage, we say that is the mark, or that is a compromised identity. So all of this actually also extends into the case where 2 to the L is exponential. Here we have to use the more sophisticated tracing algorithm developed in the work of Nishibaki, Weeks, and Zandri. There they show how to also trace for an exponentially large space by essentially reducing this tracing problem to something called the oracle jump finding problem. That same algorithm also applies if we start with a private linear constraint PRF. So I don't have time to describe it here, but everything I say does generalize to the setting where we have an exponential identity space. Here it's easier to think about and see that this works even with a polynomial identity space. Okay, great. So good. So the implication is there has to be a jump somewhere. It has to appear at the compromised identity. This allows us to extract the mark. Okay, so we now identify this intermediate primitive, this notion of a private linear constrained pseudorandom function. It suffices now to build this primitive, and we're going to show how to build it from standard private constraint PRFs. And then at the very end of this talk, I'm going to give a brief overview of how we actually realize all of these ingredients from lattice assumptions. Okay, so let's begin by starting with a standard vanilla constrained pseudorandom function. So we know how to build constrained pseudorandom functions from lattices. So circuit constrained PRFs are known. This is the Brzezinski-Bakunte-Nathan construction, which I will give an overview of at the very end of this talk. So let's just start there. So let the domain of the PRF be the same as the identity space, right? So now how do I implement this linear constraint family? Well, the linear constraint family is basically just a constraint for the comparison function. So the constraint function has an ID hardwired inside it. The ID takes an index t because the index is basically literally the domain. So of course, this doesn't satisfy the privacy requirement. The index is public right now, but let's forget about that for a moment. Let's just talk about linear constraints, right? If we just want a linear constraint, well, a circuit constraint, of course, implements a linear constraint family. So you embed the ID as part of the key. It takes as input the index. And if the ID is less than the index, the constraint is not satisfied. If the ID is bigger than the index, the constraint is satisfied. So this gives us the first requirement, linear constraint PRF. This should not be surprising. a constrained PRF for circuits, of course, implies a constrained PRF for a much simpler function family. The problem, of course, is that the indices for these domain elements are completely public, versus if you look back to our tracing construction, we require some hiding properties for these indices, even given constrained keys. But here, even without the constrained keys, you can tell what those indices are. So if we want to hide things, well, the natural thing to do in crypto is we can encrypt the indices. So now, suppose instead that we take the domain of the PRF, instead of having it just be the identity space, it will be the space of ciphertext for some symmetric encryption scheme. Okay, so take your favorite symmetric encryption scheme. The domain of our PRF will be the set of ciphertexts for that encryption scheme. So now, how do we do the constraint function? Well, the constraint function, or the constraint function that we want to handle will take as input a domain element of the PRF. What is the domain element? Well, it's a ciphertext. And basically, a domain element with index I will just be an encryption of index I for that particular under that particular encryption scheme. And this can be this should be a randomized encryption scheme. So there can be many domain elements that all have the same index, right? Basically sample some encryption randomness, encrypt the index, that's your domain element. So how do we implement this linear constraint family? Well, it's quite straightforward, right? What we would do is we take the input ciphertext, we will hardwire the decryption key for this symmetric encryption key scheme inside the constraint key. So we hardwire the decryption key, and we simply decrypt the ciphertext using the ID, and then we do the comparison exactly as before, right? So this constraint key can be used to decrypt input points that correspond to all inputs that encrypt an index that's bigger than the ID. So this exactly implements the same linear constraint family as before, except instead of having it on public indices, we have secret indices, and we use a decryption key to identify it. But here there's still a problem, because if we have a standard constraint key, it leaks the decryption key K. And why is this a problem? Well, the decryption key K is used to decrypt the encrypted indices. So therefore, if I give you, let's say, a PRF domain element with index I, well, that domain element will be an encryption of I. If my constraint key leaks the decryption key, well, then you actually recovered the index I, and this is problematic. So again, this is not a difficult problem to fix. All we need is something called a private constraint PRF. So here there's a little bit of overloading of notation or of terminology. When I say a private constraint PRF, I mean that the constraint PRF key, the constraint key itself, it hides the constraint description. So in particular, it hides the decryption key here. In a private linear constraint PRF, the privacy property is privacy for the index associated with domain elements. But using a private constraint PRF, we can actually complete this picture. If we use a private constraint PRF in conjunction with a symmetric encryption scheme, we obtain a private linear constraint PRF as follows. So why do these properties now hold? So normal hiding says that if I encrypt to index 0 or domain elements with index 0, they should be indistinguishable from random domain elements. This is okay as long as the encryption scheme has pseudorandom ciphertext, right? Then the encryption of any element will look like a uniform random string over the entire ciphertext space. So if the encryption scheme has pseudorandom ciphertexts, and as long as the constraint key hides the symmetric key or the secret key for the encryption scheme, then we can appeal to pseudorandomness of the encryption scheme to argue normal hiding. For identity hiding, this follows just directly from semantic security of the underlying encryption scheme. So domain elements with index I and J, well, why are they indistinguishable? Well, the elements correspond to the encryption of I and the encryption of J. If the encryption scheme is semantically secure and the constraint key hides a secret key, we can appeal to semantic security of the underlying encryption scheme to argue this property. And finally, pseudorandomness. Why are the PRF evaluations on inputs with the maximum index pseudorandom? This exactly follows by constraint security of the constraint PRF. Namely, if the message space of the encryption scheme is between 0 and 2 to the L minus 1, then when we decrypt, we will never produce an element that's bigger than 2 to the L. So then if the underlying constraint PRF family satisfies constraint security, namely the PRF evaluations at inputs not satisfied by the constraint are pseudorandom, then we get a pseudorandomness as well for our private linear constrained PRF family. So to summarize, how do we construct a constrained PRF? We basically showed that starting from a private constrained PRF in any symmetric encryption scheme. So in fact, private constrained PRFs imply one-way functions, which implies symmetric encryption. So technically, we just need private constrained PRF. We get a private linear constrained PRF where we have a secret sampling procedure. And this gives us a traceable pseudorandom function with secret tracing. So the secret sampling is because you need knowledge of the encryption key in order to sample, and you also need to be able to sample PRF evaluations, which require information about the secret key of the PRF. So starting from the LWE assumption, we can realize single key private constrained PRFs, which propagates through our generic transformation and gives us single key traceable PRFs. So this is exactly the same building blocks that we require for building single key watermarkable PRFs. So if we just take a look at this box right here, so LWE going to single key private constrained PRF, this goes to watermarkable PRF via previous works. In this work, we show that it also suffices to give us traceable PRFs, but now satisfying a much, much stronger notion of security compared to the previous constructions. If we want a public tracing, it turns out that this does require some additional tools. And the main difficulty is that in a public tracing scheme, we need to be able to sample PRF evaluations. So we need to be able to sample both PRF inputs as well as the outputs. Because remember, the tracing algorithm has oracle access to a distinguisher. And the input to the distinguisher needs to be inputs and output pairs from the PRF family. And so it's not just a matter of fact of replacing the symmetric encryption scheme here with a public key encryption scheme. That doesn't work, because while that solves the problem of being able to sample the inputs, it does not give us a way to sample the outputs. And in order to do this, the way that we showed in our work is we can do it from indistinguishability obfuscation together with injective one-way functions. We basically publish an obfuscated program that has the PRF key hardwired inside it that allows us to publicly sample inputs and output pairs from the PRF family. If we just use private constrained PRFs, it's not clear how to realize this. So realizing public tracing from standard assumptions or realizing it without going through I/O is an open problem. And this is also the case in the setting of watermarking. One of the advantages of the I/O construction is that it also gives us full collusion resistance. Notice here that we only get single key.
David?
Yeah.
Yeah, I was just gonna make one quick remark, if you don't like. So let's say you didn't want to use I/O, you're only okay with learning with errors. It's kind of interesting, at least to me, that you normally think of PRFs as in the normal world, as a great building block for building up symmetric key crypto and all this stuff. But it's here, and I guess we got this feedback, too, that like in the tracing world, we can only do single key. Whereas if we didn't start with PRFs, if we just built, from previous work, we just built traceable encryption directly, we can do better.
Yep, exactly.
I wonder, it almost seems like there is a message of like, maybe this isn't the right building. Maybe you should just build each primitive tracing individually and not go through the PRF route.
Right. No, that's a great point. And I think that kind of highlights some of the interesting aspects in the tracing world. So like in a standard classic symmetric encryption, you have PRF, you can get everything. But once we want like a traceable analog of these primitives, that same intuition doesn't seem to translate, because a traceable PRF, sure, implies a traceable encryption scheme, but we don't know how to build a traceable PRF with full collusion resistance, versus we do have great constructions of a traceable encryption with full collusion resistance. So that might suggest that when we look at tracer tracing for specific primitives, it might actually be more reasonable, as Brent suggests, to actually target the actual primitives we want, rather than go through the underlying, just try and do it for a building block. Of course, if we now are able to build let's say a fully collusion resistant traceable PRF, we do recover those same implications, but that seems like a much harder problem than just targeting the primitives directly. Okay, cool. So just to summarize this first part of the talk, so the main motivation that inspired us and the main message that I want you to take away from here is that the existing definitions of software watermarking, especially in the context of cryptographic functionalities, does not offer us very strong security because it imposes very significant restrictions on the adversary's capability. And the way that we address that in this work is by introducing this new notion of a traceable PRF with a much stronger notion of unremovability, which basically says that if the adversary can construct a program that allows us to break security of the underlying cryptographic primitive, namely breaking pseudorandomness, then such a program must preserve the watermark, independent of whether the program preserves input-output behavior, and so on. And I think the more general takeaway is that when we start studying these notions of traitor tracing or watermarking for these different kinds of functionalities, is we should actually think more broadly about the security of we should think more broadly about our security notions. The most natural one of sort of tying together functionality preserving to exact input-output preservation, this may actually not be the most reasonable or the most useful security notion, just because it might open us up to new adversarial strategies that are not captured by existing models. So the most natural notion and the prevailing notions that has been considered and studied previously may not be the best definitions. And I think there's a lot of value in revisiting some of those definitional foundations in order to figure out and identify what is the most reasonable or the most useful definition for studying and analyzing these kinds of primitives. And we sort of have made some progress on that in this case, watermarking PRFs by going to this traceable PRF route. And in terms of the construction side, the main intermediate primitive that we rely on is this notion of a private linear constrained PRF. And we show that starting from the LWE assumption, we can go all the way to a single key traceable PRF. So in this talk, I sort of shown the last or the two arrows in the middle, going from private constrained PRFs to private linear constrained PRFs, and then private linear constrained PRFs to traceable PRFs. And all of those details are provided in that ePrint. So any questions here? So in the remaining time I have left, I'm going to give you an overview of the first half of this transformation. So how do we actually build private constrained PRFs from LWE? This will be based on previous works by Svika and Vinod, as well as by Svika, Rotem, Vinod, and Hotek. So any questions about the traceable PRF route before I go into the more algebraic side and show how we actually construct these PRFs from lattices? Okay, so if not, let me just carry on. So this will be the lattice part of the talk, since this is a lattice seminar after all. So how do we actually build pseudorandom functions or constrained PRFs from lattices? Well, let's start from first principles, or start directly of how to build a PRF from lattice-based assumptions. So just to recall, the learning with errors assumption says if you have a uniform random matrix A and you take a noisy linear combination of the rows of A, that looks uniformly random. And then, so this assumption by itself may not seem the most conducive to constructing a pseudorandom function. Sure, it has a pseudorandomness flavor in the sense that you have something that is indistinguishable from random, but this something depends on this noise term, right? And this makes it more challenging to construct a pseudorandom function because pseudorandom functions are deterministic objects. So when constructing pseudorandom functions from lattice-based assumptions, the work of Banerjee, Pikert, and Rosen, they basically show that we can actually replace this error with a deterministic rounding step. And then we can base security on something called the learning with rounding assumption, which for certain choices of parameters P and Q, it actually reduces to LWE. So the learning with rounding assumption basically says that instead of taking the inner product between the secret LWE secret S and the matrix A and then adding noise, we're instead going to round down to a much smaller modulus P. So we're going to scale by the value P over Q over the rationals, round to the nearest integer, and that will be our value. So the noise is replaced by deterministic rounding. So once we have done this, it actually seems much more straightforward how we can realize a pseudorandom function. So let me give now the general blueprint for constructing a lattice-based pseudorandom function. So most of the existing constructions will work as follows. there will be a collection of public parameters, and these will just be public random matrices A1 up to AL. And the PRF key will be an LWE secret S. And in order to evaluate, well, we want something that looks like this. And the way that we're going to do so is the following. To evaluate at a point X, we're going to take our public parameters and our X, and there will be some procedure, some public procedure of taking X and the public parameters and deriving from them a matrix A sub X. And then the PRF evaluation with the PRF key S will just be S transpose times A rounded down. So this looks very much like an LWR instance. And the question in constructing these lattice-based PRFs is, what is the procedure that we use for this particular derivation? How do we derive a matrix A sub X from the public parameters together with X? And different works and different constructions with different properties will describe numerous ways of doing so. Here, I will just describe one particular PRFs and then private constraint PRFs. So before we do that, we need to do one more. We need one more building block, which is we have to come back to the GSW fully homomorphic encryption scheme. So the Gentry's to High Waters classic FHE scheme that has the homomorphic operations and the homomorphic properties that we need for our main constructions. So I think Hotek gave a great talk at the previous workshop going over the GSW homomorphisms. Here I will just give a very brief reminder. So in the GSW FHE scheme, the public key is just a LWE matrix A. So namely the columns of A are LWE samples. The secret key is essentially the LWE secret, and then you concatenate one at the end. The invariant and the main property that we will want is that S transpose times A, as I defined it here, is very small. It's just the error term, or approximately the zero vector. So now a ciphertext for an input X in the GSW scheme is just going to be A times R plus X times G. The important thing is that R is a random short matrix. G here is the gadget matrix. And if the ciphertext have this particular form, decryption succeeds in the standard manner. Namely, you take the inner product between the LWE secret and the ciphertext. You use the fact that S transpose times the public key vanishes, and you essentially recover X times S transpose times the gadget. And now we know that LWE, with respect to the public gadget matrix, because it has a public trapdoor, it's easy. We can actually recover X. In fact, G here has large entries, so you can actually just recover X by rounding. But again, those details are not super important. Let's just look at the algebraic structure of the FHE scheme. So the second ingredient that we need are the homomorphic properties of this encryption scheme. So in the first homomorphism, so these are the two equations that we saw from the lattice workshops a few weeks back. So the first set of homomorphisms is the public homomorphisms. So given a collection of GSW ciphertexts, there is a way to compute a GSW ciphertext for a new function f of x, right? Namely, let's say I have the encryptions of x1 up to xl. There's a public algorithm that takes in these ciphertexts and the function f and produces a sub f, which is essentially a GSW encryption of the value f of x. Okay, so there's a public algorithm that does not depend on x. So this is why I call it the input independent evaluation algorithm, because in some sense, I will view these GSW ciphertexts as encodings of the bits of x. But now there's a public algorithm that, without knowledge of the encodings of x, allows me to compute a function of x in a public manner. So it allows me to derive this matrix A sub f. And not only is this a homomorphic operation, homomorphic in the inputs, in the encoded values, it is also homomorphic in the randomness, in the encryption randomness, in a very precise form. Namely, the new encryption randomness can actually be expressed as a short linear combination of the original encryption randomness. And here, this randomness evaluation, or randomness homomorphism, will be governed by this matrix H sub f of x. Okay, so if we look at this equation, so this is the correctness requirement on a GSW encryption scheme. Namely, when I compute, when I homomorphically evaluate on these ciphertexts, I obtain an encryption of f of x with randomness r sub fx. I can now take this randomness homomorphism and essentially rearrange the equation a little bit And notice that what I will get back is something that looks like this. So this second equation here will be what I call the input independent evaluation. So it's very easy to see how to get this. You just left multiply by A, and then you use the invariant for GSW ciphertexts. Right? So basically, these two equations are the main equations that we will rely on when we construct our lattice-based PRFs. And the important thing to note here is that these two equations essentially both provide us a way to compute a common matrix A sub f, right? Here, if I know A1 up to AL and the description of the function f, I can compute A sub f. Here, if I have essentially an encoding of the bits of x, and I know this function h, or I know this matrix h, which is a function of the public matrices f and the input x, so this is why it's input dependent, I can now compute A sub f minus this additional term f of x times g. Okay, so these are the two main equations that we will use to help us build a constrained PRF. This also gives us things like attribute-based encryption. It can also be used to get homomorphic signatures and so on. All right, so let's now look at the Prekursky-Vakunthanathan construction of a lattice-based constrained pseudorandom function. So the domain of the PRF, in this case, will just be a row bit string. And we're going to use a universal circuit as part of our construction. So here I'm going to define a universal circuit that has an input x hardwired inside it. It takes in as input a description of a function f, and it computes f of x. So let's say the description length of the circuit here is exactly L. Then the public parameters of my lattice-based constrained PRF will just be matrices A1 up to AL. These will be used to encode the bits of the function f. The PRF key will just be an LWE secret. The PRF evaluation will be using that public homomorphism that I described earlier. We will take A1 up to AL and the input x, and we're going to evaluate the function u sub x, so the universal circuit with x hardwired inside it. So the PRF evaluation will be the matrix associated with the function u sub x. Okay, this is a function that depends on the input. The function that we're going to evaluate is the universal circuit evaluation. And the PRF evaluation then will just be defined as the inner product between the LWE secret, namely the PRF secret, master secret, times this matrix A sub ux. So the way that we're going to derive this matrix that we're going to multiply by is exactly using the GSW homomorphic operation. So using the input independent homomorphism. So notice that if you know x and you know the secret, you can compute this quantity. How do we constrain this function? Well, here we're going to try and build something that looks like the input independent that relies on the input dependent evaluation procedure, right? So before we showed that there are two ways of computing this quantity, A sub u of x. One is using a public evaluation. The other one will be using the input dependent or secret or private evaluation mechanism. So just a note for convention, I'm actually going to invert the convention. This is pretty standard in lattices or lattice-based constraint PRFs. We will say that the constraint is satisfied if f of x equals 0. So before I was saying that the constraint is satisfied if c of x evaluates to 1. Now I will say the constraint is satisfied if f of x evaluates to 0. The reason for this will become clear very soon. So we can evaluate at all points x in the domain where f of x equals 0. So the constraint key for a function f essentially consists of an encoding, of an LWE encoding of the function f. Okay, so the way that we encode is we just take the bits of the function f and we compute the standard GSW encodings. So A1 minus F1 times G and so on. And we're going to multiply by the PRF secret key here. So why is this useful? Let's see how we can try to use this to evaluate. So what we can do is we want to get something of the form S times A, where A depends on u sub x. So the way that we can do that, if we have an encoding, is we can multiply by the matrix H for this function u of x with the function f. So here, if we know the function f, and we know the description of u sub x, which we know because we're evaluating at the function x, we can just multiply by this evaluation matrix, this input-dependent evaluation matrix. And by the properties that I just outlined on the previous slide, this product, A1 minus F1G, this encoding multiplied by the H matrix, this gives us exactly A sub u of x minus the function f, the function u sub x evaluated on f. But u sub x evaluated on f is exactly f of x. And so we get f of x times g. And now, this is a very, very nice observation. If f of x equals 0, notice, so here we use the fact that h is also short. So error times something short is still small. So this basically is approximately the same. So this is approximately 0. So now if f of x equals 0, now this term vanishes, and we get exactly S transpose times A sub u of x. And notice that if the error is small, then it disappears when we round down. So when we reduce modulo p, and these two elements actually align. Okay, so this gives us a way to evaluate the PRF at using the constraint key. We just use the input dependent evaluation procedure. Okay, so to argue pseudo-randomness, it turns out that we have to do a little bit more work. We want to multiply by another fixed matrix. This ensures that we can appeal for pseudo-randomness of the construction. I'm not going to go into the details here, but basically the core algebraic requirements are all captured by what I have written here. There's a few additional details that we have to introduce in order to argue security formally, but I think for the general intuition, those will not be super essential. Okay, but there is a problem here, because if our goal is to build a private constraint PRF, and the reason is that in order to compute this evaluation matrix H here, this is a function that depends on the public parameters, it depends on F, and it depends on, it depends on the public parameters, it depends on the input X, and it also depends on F, the constraint function, right? In order to construct this matrix, we need to know the constraint. And so this does not give us privacy for the constraint. So the idea in the work of Brzezinski, Zabary, Vakuntanathn, and Wheat is instead of publishing the constraint in the clear, what we're going to do is we're going to encrypt the function f using an FAG scheme. And instead of evaluating u sub x directly, we're going to homomorphically evaluate the universal circuit. So let's just see what that looks like first, and then we'll see how to complete the construction, and that will conclude the talk. So instead of publishing f in the clear, what we're going to do is we're going to encrypt f using an FAG scheme. And now we can just publish the encryption of f in the clear, right? The security of the FAG scheme will allow us to hide the function f. So here, suppose that the bit length of the ciphertext that encrypts f is L. We will now define the homomorphic evaluation function that simply uses the homomorphically evaluates the universal circuit on the encrypted function f. And this will produce an encryption of f of x. So technically, this function right here does not output a bit. This function right here actually outputs a ciphertext. I'll talk a little bit about how we avoid that issue. That will not be an issue for us. Okay, so now let's just go through the previous constraint PRF construction and just replace the function f with its encryption, with its ciphertext. So we can do everything exactly as before. The constraint key will now just be an encoding of the encrypted function f. And the constrained evaluation, we can again just do exactly as before. We're going to multiply by the new evaluation function, which is a function of the homomorphic evaluation of x, as well as a ciphertext that encrypts f. So here, this only depends on public operations. This does not require knowledge of f, as long as f hat hides f. And if we just go through all of the previous steps, by the correctness of the GSW homomorphisms, the second evaluation relation, the input dependent evaluation, when we compute this quantity right here, we basically get an LWE instance where we have S transpose times A with respect to the homomorphic evaluation function. This is good. But instead of getting f of x times g, we now get the output of the homomorphic computation on g. And this is problematic for two reasons. One is this is not a bit, so the things I write here doesn't quite parse. But we can fix this part by just saying that this computes one bit of the ciphertext, and then you just compute it one bit at a time. So let's ignore that issue. The bigger issue is that this homomorphically computed quantity is an encryption of f of x. It is not equal to f of x. And the correctness requirement, the reason that the algebra worked out before, is that we said that if the constraint is satisfied, f of x equals 0, and this term vanishes. But if we have an encryption of f of x, we have an encryption of 0. Encryption of 0 is not 0, so it's not going to vanish. So we need a different idea to fix this problem. So let me first address the issue that this is not a bit. It turns out that we can actually generalize the GSW homomorphisms to matrix valued functions. So here we have the standard GSW homomorphisms: input independent evaluation, input dependent evaluation that evaluates any binary value function. Here it's actually straightforward to extend this to matrix valued functions, where we have a function f that outputs a matrix x associated with f. And instead of computing f of x times g, we compute a sub f minus a matrix x times f. I'm not going to go into details of how to do this. It turns out that you can just use the first set of equations, compute everything bit by bit, and then just sum them together using properties of the gadget matrix. So in the interest of time, I won't go into details there. Essentially, the takeaway I want you to get is that the GSW homomorphism is very naturally generalized to matrix valued functions. It's just fairly standard algebra there. Okay, so the second and a more challenging problem that we needed to fix is that instead of evaluating to f of x, the constrained evaluation is giving me a homomorphic evaluation of f of x. So I end up with an encryption of f of x rather than f of x itself. So here we're going to use one more property. We're not going to use any standard FHE scheme or any vanilla FHE scheme. We're going to use a very particular FHE scheme that has a lot of the same algebraic structure as what we're using to encode the function itself, which naturally will be the GSW full homomorphic encryption scheme. So notice that in a GSW homomorphic encryption scheme, the decryption algorithm is just computing an inner product between S and the ciphertext. And this inner product decryption procedure has the following property. If we compute the inner product of the secret key and the matrix, we end up with X, the plaintext value, times S transpose times G plus some error term, right? We end up with an encoding of X, of the encoding of X in the clear plus some error. So we will use this property to help us address the decryption challenge. Okay, so let's come back to the constrained PRF construction, where we have replaced the function with the FHE encryption of the function, replaced evaluation with homomorphic evaluation. So the first thing we're going to do is we're going to ensure that when we perform this homomorphic evaluation, the output will actually be a single GSW ciphertext. So this will not be any FHE ciphertext. So you can't put any other FHE scheme here now. We're just going to look at the GSW ciphertext, GSW scheme in particular. And we're going to define this homomorphic computation to output the actual GSW ciphertext. So now, this does not quite solve the problem of constrained evaluation quite yet. But the second thing that we will observe, and a really great insight in a work of Kursky et al., is that if we use the same secret key S here as both the PRF secret key, but not only the PRF secret key, but also the secret key for this GSW encryption scheme. So when we encrypt, this is a GSW encryption of the function f, where the secret key is actually the same secret as our PRF construction. Well, then this use of X here that I constructed is a homomorphic evaluated ciphertext. It's a GSW ciphertext that encrypts f of x. But if it's a GSW ciphertext that encrypts f of x, well, the property of the GSW encryption scheme says that if I take the inner product between the secret key and the ciphertext, I'm going to get an encoding of the actual plaintext value. What does that encoding look like? Well, it's f of x times S transpose G plus some error. So we just replace S transpose times this GSW ciphertext here with the GSW decryption relation. Lo and behold, we get exactly what we wanted from the original Kursky-Vaikunthanathan constrained PRF construction. Namely, we get S transpose times the matrix. So this is the real PRF evaluation times f of x times S transpose G. Once again, if f of x equals 0, this term vanishes and we recover the real PRF evaluation. So some tweaks are again needed to argue security. We need to multiply by an additional matrix here to re-randomize things and ensure constrained security. There's also a somewhat delicate argument to make sure that we can reuse the secret key for the PRF and for the GSW encryption scheme. So I'll refer to their paper for the full details there. But I hope this gives you a flavor for how we construct private constrained PRFs from lattice assumptions. So just to summarize the second part of the talk, everything here was predicated on two main equations, as usual for a lot of these modern lattice constructions derived from the GSW/Bonnet et al. Type homomorphisms. The first equation is the input independent evaluation. This is the GSW homomorphism. And then there's an input dependent evaluation that allows us to homomorphically compute functions on encoded values. If we view GSW/ the BGG plus through this lens, well, then the first equation gives us PRF evaluation. The second equation gives us constrained evaluation. And to argue to get a private constrained PRF, so here by itself, this combined with universal circuits, this gives you a single key lattice-based constrained PRF. To get privacy, the two main ideas is we first encrypt the constraint using the GSW FHE scheme. And then we use this very, very clever dual use idea where the same LWE secret is used for both the PRF secret key as well as the FHE secret key. And then that will actually allow us to get exactly the right algebraic structure to recover the constrained PRF or the constrained evaluations procedure of previous constrained PRFs, and hence give us a private constrained PRFs from standard lattice assumptions. And with that, I'll conclude. So hopefully that gives you a flavor for how we build private constrained PRFs. And given private constrained PRFs, you can instantiate our framework in the first part of this talk and actually build a traceable PRF that gives you very strong properties against adversaries that might try to break the PRF. Thanks.
All right. Thank you, David, for the wonderful talk. And people to hello. Yeah. So yeah, if people have any questions now, feel free to ask questions in the chat or just unmute yourself. Maybe I'll just stop the recording for now.